In this lecture, we're going to talk about the chain rule. So, chain rule necessarily involves the composition of functions. I know you don't like to hear that, but we just do it. We'll look at it carefully and you'll see how it works out. So, for composition of functions, here's graphically what's going to happen. The function g is going to take a value from the x variable, and it's going to give us a value for the y variable. I'm going to plug that value into the function f and get the result. And this function h is a composition of f composed with g, or f of g. Okay? And here's a typical example. I have, this function h takes a value from x, right? And this is the rule, and it returns a value z, whatever. These are just spaces. Okay? Okay, so h is, generally you don't know h, right? It's made up of, well, you know, but it's made up of a composition of f and g, and we're going to need to know what these functions are. So g is taking that x value, using the rule, and returning a y value. So I'm getting a y value out of that. That y value then I'm going to stick into the function f, and I'm going to return a z value, which is then this should be the same. Now, in the specific case, I have x equals 1. I'm going to plug that in and get a y value. I just plug it into the rule, get a y value 2. Okay, and then I'm going to take that 2 and plug it into this function f and get the z value. And that's the same as I would have gotten directly. Okay, usually, again, you'll see how we're going to use this. Graphically, this is what I have. I have x equals 1. I plug it into, remember, so g is a function, so there's an xy pair. I know there's a y value. Right? That's guaranteed because g is a function. Right? So now f is a function. I take that y value. It's a function, so I know there's a pair, y-z pairing. I get a value there. And notice, it's the same as I would have got directly from the function h. Right? So I'm constructing h, the h value, a z value from the parts. And that's the idea. Okay, there's a lot of arrows here. So the chain rule is going to look like this. So if we have function, compositional function, h equals f composed with g, or f of g, we know its derivative. Now notice, in order to get the derivative with respect of h with respect to x, I need the derivative of the function f with respect to its variable. And see, this is why I like this notation. It is calculus of a single variable, but that variable changes with the functions. F is going to be a function of y, right? So I need its derivative. And g is going to be a function of x, and I'm going to need its derivative. And that's why you're talking about chain rule. You're linking these derivatives in a chain. Right? You're linking these derivatives in a chain. Now let's look at let's start with a preliminary problem. Okay, the first step is, this is kind of the backwards problem, but it helps you, it'll help us get the feel for how we're actually going to use the chain rule. Notice this is the actual chain rule, right? It's a chain because f and g look like they're linked in a chain, right? I mean, that's where the terminology comes from. So it's a rule for differentiating functions that look like this. So you have to have composition of functions to use the chain rule. Again, you can see what we're going to have. If we take the derivative of this composition of functions, we have the derivative of this function. And again, it is calculus of a single variable, but that variable changes, right? The variable associated with the function f is y. So this is why I like this notation. This kind of gets lost when you just memorize tons and tons of formulas, because this is what you're doing. And notice there's the function, the derivative of the function g. So you're multiplying their derivatives together, but you're evaluating them, well, at their appropriate values, appropriate points. Okay, so again, when you're using chain rule, you're using composition of functions. But again, this is a preliminary problem. It's kind of backwards, and we'll see that in the next example. Okay, so I have my function, and we're going to do this much more carefully in the problem section next. This was like an early version of the notes. The problems came later. Here's my function fy. I just gave it to you, f of y. Notice the function, it is a function of a single variable, but that variable is y. So I'm just going to take its derivative, right? I'm just going to take its derivative with that variable, and I have it here. And I need this just for the chain rule formula, okay? And I have g, again, g is a function of a single variable, but that variable is x. And again, if you go back and review the composition and the graphs I did in the previous section, this is where it comes from. Again, often when people teach it or when it's written up, people try to suppress this. I don't think it's that difficult. I mean, this is just my way of presenting the material. It's not that bad, I think. Just look at it and it goes. So I'm just going to take the derivative of this function. Its variable is x. Okay, and I have that. And I'm ready to go. Okay, here's my data listed over here. Here's my function f, variables y. Here's the derivative fy. Here's my function g. Here's its derivative. And we're just going to directly substitute it right into this formula, right? Again, you can have your style here, but I just substitute the derivative gx in here. I substitute in g of x right here. And I just have to evaluate this function at this value, at this. And people get intimidated with this. We'll explore this more again in the problem section. And you see, it's a very methodical way of doing it. So essentially, again, y is a box. Anywhere there's a y, I'm just going to cut and paste this expression, and that's how I get this. Okay? And simplify. And we're going to look at this much more carefully again in the problem section. So just go with me here. Okay. Now here's how the problem is usually stated. Okay? I just give you this function h. Notice, how do I know I need the chain rule? Well, look at your cheat sheet, the crib sheet, I mean. There's no rule that works for this. The only rule possibly that could work for this function rule is the chain rule, just by the process of elimination. That's it. That's the only rule that could work. So I know I'm looking at the chain rule. It's the only rule that works. So I know I need composition of functions. I have to find the functions f and g. Again, it's a very, very fixed process. Once you get the hang of it, you can do anything. So I need to find the functions f and g, and usually you just have to guess what they are. Now, of course, I picked this so they were last, the same as the last problem, just to facilitate this. But when we work out the problems, you'll see there's a well-defined way of doing this. Most problems you have no flexibility. And we'll just work out a lot of problems and you'll get the hang of it. So f is a function of y, and g is a function of x. Again, the output of g is y, and this gets substituted into the function f. This is a typo. There shouldn't be two f's here. And again, this can be a little tricky. I get it. I mean, I do. We'll practice it, but I think you'll get the hang of it if you try it all. I mean, really, it is. Again, I have to have composition of functions if I'm using the chain rule, right? And you can check that it all works out. I'm going to substitute the rule in, and it all works out, right? Again, you should think of the variable y is a box. Something gets plugged into that box. Okay, and we'll explore this more later. Here's my chain rule formula, right? Here again, this implies the chain, right? That's where it comes from. So I'm basically splitting the derivatives up and multiplying them together and evaluating with appropriate value. That's the idea. And again, y is g of x. Well, let's just apply it. Now, in order to do this, I needed the two derivatives, and I just took them here. Now, I'm just writing it down quickly because we did this in the last example, right? That's why I did that example. But it's just a power rule, right? Simple, straightforward. And now I'm just going to plug the data in here, right? And this, again, is exactly how I did it in the previous steps. The difference here was that we had to guess f and g first. And you notice in the previous example, I just gave you the f and g. And again, when we work out problems in the next lecture, you'll see how you can guess f and g. Again, it's not 100%, but it's 99.9%. You know, it's pretty straightforward. We'll see. Okay? And this is how we're basically going to do it. And I'll be much more organized again in the problem working out aspect. Now, you can stop here for chain rule, right? Standard chain rule. But the next example is implicit differentiation is chain rule. Now we're going to spend a couple lectures just working on chain rule problems, and then we're going to come back and work on a number of problems on implicit differentiation. But implicit differentiation is chain rule, right? So let me just explain this again. If you want to pause and come back when we start on implicit differentiation problems, that's perfectly fine. The key feature here, remember what a function is. You have to tell me a domain. So for every x value in that domain, I guarantee you that I can give you a y value. And I associate that y value with the value of the function. So the notation is y is g of x. I'm going to call it g of x because we're going to chain row f of g. Okay, so here I'm telling you a point, and I'm saying there is some neighborhood around that point. That's my domain, some xy pair around this point. How big, I'm not saying. They're just, one exists. Right? So I know there's one value of the function. When x is 2, g of 2 is minus 1. Now notice, I'm saying there is a function. Now we did some of this in the first lecture, very first lecture on functions. We looked at the square root and logarithmic and log functions, log base 2. Those are implicitly defined functions, right? Those are implicitly defined functions. So in order to get the y value, I have to satisfy this equation, this algebraic equation, right? And what I'm really trying to do is, I don't know what that function is, but I can find its derivative, remarkably, and even though I don't know the function, I can replace it with the linear approximation. Right? So I don't know what I can't write it out. It's implicitly defined by this algebraic equation in the neighborhood of this point. Or if I want better than the linear approximation, I can use a Taylor polynomial approximation. And again, we'll explore this in sections later, but that's why this is important. In reality, in practice, I don't have a function defined implicitly by an algebraic equation. I have a function defined implicitly by a differential equation. So an equation also involving derivatives, conservation of mass momentum energy. That's the fundamental theorem of calculus. So that's really the big game. We're just starting here. But this is useful in its own right. So how do we do it? Why is this implicit? Notice this is the picture. You could solve this and get y equals, right? X minus 1 square root, right? Whatever. But it's not easy. It's not necessarily easier to do it, and there are problems where you simply can't. Again, we'll look at this. Implicit is nothing to be afraid of. Here's my point. Notice my function is only this bottom piece. That's specified because I have the point. Now, you don't know this picture, and I'm going to take a neighborhood here. Notice my neighborhood is really the lower quadrant here, and even though generally I don't know the function, okay, and this is a special case. I'm going to replace it by its linear approximation, or if I want more accuracy, higher order Taylor approximations. So that's the idea. Now the problem people have is they solve it for y, and then they think they have the function. But notice, you have the wrong point. So you get the tangent line, you get a slope here and the tangent line up here, and none of it makes sense, and you think it's a trick. It's not a trick. You are forcing it to do this, right? So this is where you get into, well, the square root in this case is the negative. You're just not doing it the right way. You're not thinking about it in the correct way. Could you jury rig this? Yes, but why? Okay, so let's just look at it. I can't take the derivative of an equation. I need functions. Now, again, people do this and they tick everything. That's just shorthand for what I'm doing here. So again, if you do this for a living, I mean, maybe that's a good shortcut for you. But I think generally speaking, until you get to be a pro at it, why take the shortcuts? I need functions. If I'm doing calculus, I need a function. So all I'm going to do is replace y with g of x, right? That's it. And now I'll take the derivative. So notice this is what we did before. So if we had, say, f of x equals x squared, we'd have the derivative f of x on this side, the derivative of x squared on this side. This is just a generalization of that. Again, I don't need to always reinvent the wheel. I'm just going to apply those techniques and expand it out a little bit. Now just look at it. What rules are you going to use? Well, just looking at it, 0 is a constant, so the derivative of a constant is 0. Notice it's not 0 because it's 0. 0 is a constant, right? The function on this side is f of x equals 0. So the derivative of a constant is 0. Over on this side, don't stress about this. We're going to do a lot of problems with this later, and we'll talk about it. But don't worry about it. What's the most obvious rule? You have a sum and difference rule, right? Here's a difference, here's a sum. So just do the obvious things. We'll worry about this later. Don't get excited about it. Take care of the easy terms, right? Derivative of 0 is 0. It's a constant. Derivative of 1 is 0. Again, I'm not writing it all out anymore. We can do this. We have bigger problems. X to the first power derivative of x is 1. So all we have is this. This is my expression. So let's put all our attention now and look at that term. Right? So let's look at this term. I'm going to guess, again, we're going to look at this very carefully. We're going to do a lot of problems like this. I'm going to guess the inside function is g of x. And again, what can you do with that? Just leave it alone. Again, we'll talk about this at great length. The outside function is y squared, and it all works out. I'm just going through the motions here to show you how this is going to work. We'll look at it very, very carefully. Once I have the functions f and y, I take its derivative, right? Now, so I'm just going to say that g of x squared is a chain rule, right? The outside function is y squared. The inside function is just leave it as gx. I'm just going to write it out, plug everything in, and it's done. Now again, I want to emphasize, I'm being kind of casual about this. I'm just implying that implicit differentiation chain rule. I have a lecture, it's actually a long lecture, it breaks into 2 lectures in the lecture format in the class. So we're going to do a lot of problems on this, do it in the lab. So again, we'll do it very, very carefully. I'm just kind of going over it very quickly here in a cursory fashion. So now I come back, this is where I left off, and notice I just plug and chug. I do this formula on the right, I just plug it in, and that's it. I have the derivative. And of course, once I have the derivative, I can find the slope of the tangent line. And again, this is kind of a preliminary version of the notes. We'll be very careful about it. So I can evaluate my derivative at that point, and I get the slope of the tangent line is minus 1/2. Okay, and this is how we're going to do it. Once I have the slope of the tangent line at the point, I can come up with the tangent line, the linear approximation. I can take its second derivative, come up with the second Taylor polynomial, the third Taylor polynomial, and so forth. Okay? And here's a picture. Determine the tangent line. So as long as I have the slope and the point, I'm fine, right? There's my slope. There's my point. Just plug it in. Right? Pause, you can see, but it should be very routine. I plug it in, and well, back to my picture. This is my picture. That's my point. Generally, I wouldn't even know this. Notice this curve does not define a function, right? A function has to have for every x, there's one y value. I define the function in a neighborhood of this point. In this case, the neighborhood would be the whole fourth quadrant, but a neighborhood generally of this point. And again, notice generally I can't write out what that function would be explicitly, but I can approximate it with its tangent line or its Taylor polynomial. And that's the idea. Okay, so you might come back to this, that's fine. We're going to look at more chain rule problems next, a lot of chain rule problems, and then we're going to come back to linear approximation. All right.